Yeah, I
Can
was
you,
wondering if that was just me. I couldn't hear him.
All right, let's try
Brad?
that again.
We can hear you
Okay,
now.
okay, starting over. All right, so I'm Brad Nelson, uh, fourth tinkerer, and today I'm going to present a talk on µEforth and the Pico-iCE. What prompted this talk was back on fourth day, back in November, Christopher Lozinski generously gifted me a Pico-iCE. Of course, my first thought was to put forth on it. I'll confess that I had not previously been paying a lot of attention to Raspberry Pi Pico. A lot of my focus has been on the ESP32 family of devices, and so I was relatively unfamiliar with this this family of devices. This particular device is really kind of cool. It's got a both the chip on the Raspberry Pi Pico, the RP2040, as well as the ICE 40, which is one of a handful of FPGAs that is got a format that's open source and sort of known. It's got quite a lot of ancillary storage and
Brad, can you please mute?
sorry, what's that? It's got a range of different interesting additional storage. And one of the neat things about it is that it sort of opens up all the pins in the device, and both the FPGA pins and the RP2040. There's a separate piece of 4 MB flash storage for both the CPU and for the FPGA. There's an SPI RAM that's available for use, I guess by either, although I think it's modulated by the CPU. There's a shared LED, 2 push buttons, and the really cool thing is that the FPGA has kind of got all of its external control pins under the control of the CPU, so you can sort of stop it and start it and control its clock and even feed its configuration RAM from the CPU. So lot you can do there. The RP2040 is this dual ARM Cortex M0. It's got some onboard RAM. It's got a lot of I/O pins, including some that can be analog. It's got capability of a bunch of UARTs and SPI controllers and so on, a bunch of PWM channels, and one of the more interesting things is that there's a programmable input-output interface to the chip that is actually what's used to build up a lot of these external interfaces. And so it does a thing that makes it kind of convenient in comparison to the ESP32, which is that it can boot up over SPI or USB, and has some interesting ways that you can program it. The programmable input-output system is sort of there's 8 instances of it, but it's really 2 separate units with 4 sets of shift registers and state machines each. And it's meant to be something that provides the board with a lot of I/O flexibility, almost like you sort of had an FPGA on the pins, which you do also but it also gives you sort of an interface that is easy to build up for common protocols, or apparently you can even get it to do DVI or VGA. The way it works is that there is a small bank of 32 instructions. So each of the 2 units has 32 instruction slots. And then there are 4 separate state machines that are independently executing the program in that same instruction memory. And then they each have a shift register FIFO for streaming things in and out. And they can use this to very carefully match the clock edges and so on in different input-output protocols. It's as I said, there's these shift registers coming in. There's 2 scratch registers, so it's almost like a little miniature computer with a small program on it. And then there's independent clocks for each of the different the 8 separate state machines, and then it even interacts with the IRQs in the system. So this is sort of the state that you get. There's a program counter and then these 2 scratch registers, and the instruction set lets you set up like a simple loop, and you can here this is just a square wave, but you can do kind of all the low-level plumbing that you would need to implement something like SPI or very likely even more complicated protocols. The instruction set is simple enough that if I get around to playing with this, almost certainly I'll make a little inline assembler for it in Forth. This is the whole instruction set. There's 16-bit instructions, 5-bit addresses, and okay, something's going on the Zoom here. I think we have a moderation issue, perhaps. I'm gonna pause.
It says it's Brandon Smith's page or Brandon Smith's screen.
We boot him off. He's gone.
Okay, moving on. Yeah, so there's quite a bit of flexibility in the instruction. Oops, I need to represent. When did my slides kick out? Okay, I'll resume. So there's this flexible instruction set, and it can implement simple protocols and loops and so on. The instruction set is got 16-bit instructions, and you've got 32 address slots to work with. There's a conditional jump. There's operations to shift data in and out of the shift registers and to control the value of different pins. You can actually there's this delay side set which allows you to if you need some very precise timing on the protocol you're implemented, you can arrange so that at a particular instruction, multiple signals will make a transition all at the same moment to allow you to have very precise edges sort of right up to the clock speed of the chip. So lots of flexibility, and it's used to build up a lot of the external I/O on the thing. Then there's the FPGA, which is cool and novel in its own right. There's a 52,000 LUTs for the µEforth. There's a large bank of memory that's attached to this FPGA, and then there's a bunch of inline dual RAM. We'll look at the layout of it internally later, and then there's a bunch of DSP blocks. So this is kind of the general shape of the FPGA. It lets you, there's a sea of LUTs that are in a grid, and then some bands of RAM, dual port RAM in between, and then sitting around the edge, some single ported RAM and a bunch of I/O and the DSPs.
Brad?
Yes.
Can you tell me, for those of us that are used to building computers with stone knives and bit slice, how many LUTs is that? For example, how many LUTs is like a Bowman fourth engine?
So I believe Bowman's smallest one is very small. It's like 160, something like that. I think you need maybe some external RAM to go with it. So you'd have 160 LUTs compared with now that's a really, like the J1 is a really tight device. This is more like up in the realm of you could, squeeze in a small a small, more complex thing like maybe some derivative of a part of the ARM instruction set if you really stretched it. But I'm not an FPGA expert, so I would defer to folks that have done more playing with the tooling and Verilog and seeing what you can squeeze into space. I think the other thing is that I'm sure it depends a little on the efficiency of how well you pack things in and map it to the architecture. If you, for example, can take advantage of the DSPs to do to do a multiply that matches the thing you're trying to build, then it will be more likely to fit versus if you have to build the whole thing out of LUTs. So, did that answer your question, Kevin?
Yeah, that's fine to the extent that I. Yes, fine. Thanks.
Okay, no worries. The LUTs are arranged in these chunks of 8 bits at a shot. So you've got imagine a 4-bit lookup table, and then a set of 8 of them arranged in a chain. There's configuration that allows you to turn on a ripple carry within the block of 8. And then you choose the 16 bits that define the lookup table, and then you can optionally turn on a flip flop for each of these. So it's sort of, in one sense it's just a sea of raw gates for you to use at your disposal. As I mentioned, there's these flexible DSPs that are basically they're multiply accumulators that you can string together in various ways to produce a variety of different combinations of multiply, accumulate, or subtraction. And there's the diagram, which I don't expect you to go through the diagram. There are these flexible I/O pins as well that give the FPGA quite a bit of fine-grained control if you wanted to individually enable and disable the particular pin, have it float, have it go in. But all this, to be clear, is sort of digital stuff. The RAM blocks, they're dual ported sort of read-write chunks of RAM that you can use sitting throughout the chip. And then there's the single ported RAM on the periphery. Programming the Pico-iCE, the path that I stumbled upon initially is that the Pico-iCE SDK is built on top of the SDK that's kind of the main SDK for the Raspberry Pi Pico. It has a really interesting method of flashing the device that I had not encountered before, I think called UF2, that I'll talk about in a sec. And then it has the ability, because it's got sort of a proper USB interface, to actually create multiple virtual serial devices. So where some of the ESP32 family, you'll plug it in and you'll get a serial port, but it's sort of it's fixed as a serial device. Here you can, the device can appear to be a flash drive or appear to be multiple separate COM ports, things like that. The flashing is neat. It's there's this protocol apparently comes from Microsoft, where it's sort of a little bit of a clever hack to match up with the capabilities / limitations of the FAT file system versus sort of the desire to flash things in chunks. So when you're operating over USB, you do things in chunks of 512 bytes, and FAT happens to have blocks that are 512 bytes, and so you can be guaranteed that you sort of either atomically receive 512 bytes in total or not. And so the format is structured around including a small header and then some address information, and then basically breaking it up into a series of chunked writes to the device. What this does is it means that you can basically put the device into programming mode, which you do by attaching two of the pins together and hitting reset. And then when it's plugged in, it will come up with a flash drive that's mounted, and you simply drag the file that you want to program onto the device. You don't need any special tooling, just a USB port to plug it in, and you can program the device, which is kind of neat. In contrast to say something like ESP32, where you need some tool that knows how to talk to it at a low level. That's the device. I've one of the forths that I've put out there and have gotten a few folks to care about a little bit is µEforth. It's an indirect threaded forth that's written in C. It uses a thing called X macros extensively to try to make it very easy to expand and sort of dense, almost in a forth-like way. I've ported it now to a bunch of different things that originally started out with the goal of being for ESP32. There's a Linux POSIX variant. There's Windows support. On those platforms, I try to make the way that it loads very minimalistic, so that it basically has only like a handful of symbols like DLSym, and then Dynet uses dynamic linking to pull everything in. For ESP32, all of the bindings need to be sort of explicitly pulled in, and then there's also a web version that you can try. All of this is at eForth.appspot.com, and so why not the Pico-iCE? X macros, just in case, folks, that's a weird one to throw out there. It's a C preprocessor trick that lets you build up lists of data that you then in turn use to build code. So it's kind of a form of metaprogramming. You sort of make the caller a parameter. So what's neat about this is that all the primitive words in µEforth, by and large, are defined in a single line. A syntax basically just like this is used to declare each of the words that gets injected into the forth system, and then a couple of tables of type definitions and sort of initializations of memory and so on are done reusing that same list multiple times. So adding a new word to the system is a one-liner, but then it gets used in multiple places. So it can be as simple as the name and then what the word does to add something to it.
Real quickly, could you explain the difference between the X and the Y macro?
Sure. So this is just a convenience. At its base, the system actually originally it used macros that had an X in them, and the term X macro is the name for the general approach, but people use all kinds of conventions in terms of typically they'll choose a one letter name for the different for the element that you're going to redefine when you want to apply the list in multiple places. In µEforth, because there are a lot of words that get defined, especially for all the ESP32 bindings, I found it's convenient to have some predefined variants that expand out one extra step to save a few characters. So the X macro allows the one that's like the add word allows the definition of a name that has characters that are not valid C identifiers, and in that case, the second parameter needs to be a valid C identifier, because there's a few places when I'm expanding out the set of forth words that I have to have a uniquely valid C identifier. So if you have a word that has a punctuation character in it, you need to give the string a name that is unique in the whole system made up for it, and then what the word does. And that the Y macro is a shorthand, so that in the case that you have a word where all of the characters in it are valid C characters, then you can just use the terser syntax, and it will expand it out into the other one. And there's one layer of extra complexity there, which is at some point I added vocabularies, and so there's another layer underneath where these are in fact actually shortcuts on top of some macros that end with a V that also include expanding out things that are in a vocabulary. So this is how you would add words to the forth vocabulary. But if you wanted to add it to other vocabularies, you need some of those macros. So it's grown a little bit in complexity. Originally, it was they were all just X's, but I found that as I grew, it was easier to not have mistakes where have one or the other not match. So, cool. So importing µEforth, what I did was followed what the SDK sort of seemed to suggest was the typical pattern. For some of the other platforms, I've for ESP32 for example, I'd leaned into the Arduino tools mainly as a distribution aid, because that allowed me to distribute a single INO file, and then somebody who's got that tool can install it. But because there's this UF2 option for distribution, it's really convenient. You can simply distribute a binary, and somebody can drag and drop it into their board. And so for that reason, I looked at the SDK. I added the Pico-iCE SDK and the Pico SDK as submodules to the µEforth project, and then I hooked in the CMake build there. And normally I use just ordinary make in for the µEforth build, but I just go ahead and invoke CMake underneath. I found so all the other flavors of µEforth have fault handling. I initially, in bringing it, this is the first new platform I've brought up since adding fault handling. So I found that it actually got in the way. I didn't want to have to sort out fault handling before I could bring the thing up. So I disabled fault handling for this device, and then found that I was able to, more or less follow the architectural plan I had in place. Add a new header for some built-ins, a new main to do some of the initialization, but then although it built, it didn't run. So debugging is always a little bit of a challenge in bring up on boards. I kind of rewound back and confirmed that I could build one of the IO samples, and that they built and deployed to the board, and that worked fine. So then I did a thing that I have done primarily for testing purposes for ESP32, but I added a simulation variant, which is basically just a version that is building for Linux, but brings in all of the same Forth startup and the same sort of assumptions about which words are predefined. And I found fairly easily that once I had done this, that I had had a couple of errors in terms of the dependencies that I had assumed. This is a problem I think I need to sort out long term with µEforth. It currently does a lot of the I/O and using deferred words, so that until those words have been defined, if you get any error messages, they will crash the system or go off into oblivion. And so all that was happening is I was getting an error that if it was going somewhere reasonable would have told me what was going on, but I couldn't see it because it was going off into oblivion. And then it came up, which was surprisingly easy. So I then added some bindings for some of the basic things that the system needs to sort of function, and then I added some bindings for all of the ICE specific stuff in the SDK, just because there was a very small list of them. I've recently, like last night, started on adding some of the Pico bindings for the Pico specific interfaces. I added the ADD or ADC interface. There's a bunch of other ones. They're a little bit more complicated, so it will take some time. But there's unlike ESP32, where actually, I shouldn't assume that there aren't libraries for this device. I'm sure they're all. In fact, I'm quite sure the opposite. There almost certainly are. But there seem to be at least a canonical set of a small canonical set of hardware-specific interfaces. And my current thought is that I'll make those kind of built-in bindings. But more to come there. One issue I've run into is that this whole sort of setup with the submodules is a little slow. I found that if I did the submodules as a shallow submodule and then only initialize the ones that are needed, and then only build the target and not sort of the transitive set of things that CMake will barf up, that it's faster. Using Ninja is a good bit faster. It's helped some in fairness, it's not that the ESP32 build is particularly fast. It's just anything that's not, a native build on your host is bound to be slow. I think I've put it in enough of an optional state that if anybody is checking out the repo and building directly, it won't be too much in their way. But send me mail if that's not the case. I've refactored the documentation to include information on it. So if you're, this is for those of you that haven't seen this is the µEforth website, and there's now a tab for Pico-iCE, and has information about how you would flash it. And some of the documentation is shared and generated from a common thing. There's I don't claim that it's exhaustive, but it is what it is. There's I documented to a limited extent the bindings that are there. For now, I haven't all of the branches that I have for the stable versions of ESP32 don't have this on it, so it's in beta for now. And I don't publish by default because it's a little bit slow to push it. But so what's next? The USB bindings are pretty cool. Like it's nice to have a device that it's not just sort of possible, but is easy and straightforward to do things like create a flash device. I was impressed. One of the I think that the default firmware for the Pico-iCE actually kind of doubles down the layering with UF2, so that by default it will mount a flash drive that you can copy an FPGA image onto, and then if you attach the pins, then you get the one for the microcontroller, which it's a pretty neat pattern to be able to mount flash storage, and it means you don't have to have special software there. Almost certainly will finish the hardware bindings. The FPGA flash is sitting there empty, and there's kind of unlike ESP32, I'm always kind of scared that I'm going to tromp on something from the Arduino tools if I mess around with relying on the flash. But here I feel like I could safely assume one of the flashes or the other. I could carve out some blocks and use it for block storage. It might be possible to build with Arduino as well, or instead. That would make it easier for folks to add their own bindings. So I might go there if it looks like it's not too hard to. I had missed that there was an Arduino tool chain for it, so that's an interesting path, and I'll have to try it at some point and benchmark it. If it builds faster, that might be the tiebreaker. And then an aspirational thing that's still mostly an idea in my head, but I've been doing sort of investigation in that direction, is to be able to synthesize for the FPGA eForth on device is sort of the goal that I have in mind. I don't know that I have a particular thing to do with it in mind, other than that it would be cool. The µEforth is cool because it's got one of the few bitstream formats that's been fully reverse engineered. There's an open source Verilog implementation, and the IcePack tool captures the sort of how simple the config is. So each of the LUTs in the device has a small handful of bits that define the lookup table, that define which things are enabled. And then you have this sort of sea of LUTs, and then these yellow bands are where the dual-ported RAM is at, and then the I/O pins are around the periphery. In this structure, there's a lot of repetition. There's a lot of even the RAM cells use the same routing structure as the LUT blocks do. The logic tile blocks. By the way, this is there's a great, somebody's made an online viewer that lets you visualize the chip and zoom in and out in various ways. There is a weird quirk where for whatever reason, the FPGA has some kind of a reflection symmetry, so that the different, I had found a picture online of this and then failed to take a note of where it was and couldn't find it back for the presentation, but there's each of the four sides, the configuration bits flow in kind of flipped, and this is captured in the IcePack tool. That there's this sort of mirror reflection to get the layout, and then within each of the tiles, there's some number of bits that determine the lookup table, and then the rest are for routing. The routing logic, I think I'm starting to understand the patterns to it, but I haven't quite gotten my head around all of the intricacies of what it would take to generate it sort of on the fly. There's this regular structure where there's a flow of 8 bits that get shifted, that over the course of 4 cells will get shifted over or connected over 4 of them, and then vertically the same thing, and then there's a one to the right that is has a shift to 1. So there's a kind of a dispatch network that is very regular, and then within each cell you can choose basically 16 connections that you make to these. So it's not a colossally difficult thing to do routing for. Obviously it would be something where you would, if you were doing it just kind of greedily, you wouldn't get a great synthesis, but it would at least be something that you could do interactively, which is, I think, the thing I would love to be able to create a new description of a thing, hit enter, and boom, it's there, and interact with it. So we'll see. It doesn't allow partial reconfiguration. You have to reconfigure the entire thing, but you can kind of pause the clock while you do it. So with a microcontroller in there, lots of possibilities. And so I have some vague idea of the vocabulary I might use for it. Basically, I'll have some syntax to describe bundling up of chaining together wires into buses, and probably what will happen is, to make layout possible, I'll have to have some kind of a hint to tell it where to place it, so that it doesn't have to smartly figure out what to do if it paints itself into a corner. And then build up basic gates and maybe adders or whatnot, although that wouldn't use the built-in ripple carry. And then I think there's a pattern that can be used to do all this, but this is all future-facing and vaporware, so I'm not going to spend too much time talking about it till I've got something cool to show. So with that, I will pop out and do a very brief demo. I'm plugging the board in, and I'm going to actually focus what I'll do is I'll go ahead and fire up a copy of PuTTY, and I'm going to, just so folks can see it better, I'm going to zoom in on PuTTY, and so it is µEforth, and has the usual things, but there are these 2 additional vocabularies, this Pico one that I mentioned, where I've just started to add the ADC stuff, and then there's the ICE vocabulary, which has a bunch of different operations. The one I'm, for this dynamic flash stuff, the fact that there's this ICE CRAM open and read and write, or sorry, write and close is neat. These first 3 here, because what this means is that I can create a bit stream for the flash, and then serialize it over and feed it on startup, and then the FPGA can be started and stopped. Let's see, some simple things I can show. So the FPGA has the flash for it has not been reprogrammed since I put one of the samples on it, because the µEforth is just sitting on the flash chip that has is used by the microcontroller. So I can do ICE FPGA start, and then it will start the sample that was on the FPGA, which just oscillates through and changes the color of the shared LED. I can then do FPGA stop, and that will stop that program. If I can type with one hand. There's also the LED. There's a separate set of routines to control it from the microcontroller. So I can initialize it, and then you'll notice it goes dark. And then if I do ice LED green, I can turn on the green LED, and ice LED blue, and turn on the blue one, and then you get cyan. It has all of the usual things there. It kind of because it's written in C, most of the things came for free. I haven't looked at how good the code gen is. I'm sure for some of it it's probably dreadful, but I've tried to construct µEforth in a way that it doesn't do too terrible a job generally, and I haven't been too horrified with the output. For some of the operations like /mod, probably it's not doing the optimum thing underneath. I've tried there to focus as much as I can on correctness. There's a floating point stack. But it is a single precision floating point stack. Be aware. That's just a legacy of I did what the ESP32 hardware could support, and had some other projects in mind that needed single precision, and haven't figure if you need double precision, you should be using integers and doing something else. So in any event, that's it. If there are any questions, I will take your questions now.
Can you hear me?
We can hear you.
Great. First of all, thank you so much for doing this. Really appreciate it. How large is your executable?
That is a good question. Let me go and answer that question real time as best as I can. So this is the build output, and let's take a look here. So it looks like the binder itself, I don't know if that's the right piece, is 85K. I suspect that it's baking in a lot of the standard library into it, just because of the dependencies, but I'm not sure. This isn't a shocking figure, given that one of the things that µEforth does in general is that a lot of it, I originally tried to write it with a very small kernel of words that were not implemented in Forth, and I've gradually veered away from that because it was starting to cause sort of capacity problems in ESP32, but there's still a lot of it there. So like I'm going to do the scary thing of opening a gigantic binary file in VI, but if you scroll down here, you'll notice that as you get into the content of the file, a lot of it literally is Forth code, because at boot up it is compiling a good chunk of the system. So I suspect that figure is at least close to the mark, because I know that ESP32 Forth ends up being kind of in a similar ballpark. So does that answer your question?
Yeah, and so just for the context, the RP2040 has some 264, I think it's kilobytes of memory, and so that's like 1/3 of it or 1/4 of it. So great. Next question, if no one else is. I don't know if you've messed much with this USB stuff. If I ever were to run multiple Forth cores on the FPGA, I'd love to be able to pass through like a UART, two different UARTs. Can I do that with your stuff?
So currently, what I've done in the startup code is that I've specified a call to the there's an initialization routine that spins up a single UART for standard in and standard out, and there is actually a more complicated call that can create several UARTs at once, and you can kind of map them individually. The call to them is complicated enough that I wanted to take a beat and look at it and understand. Ideally, what I would prefer is to be able to dynamically turn on and off the individual interfaces, but at least the wrapper that some of the samples use appears to assume that you're going to have like a static configuration that you put in and then sort of do once. And so I'm hoping that there's a way to kind of dynamically say, okay, let me start up and I've got one interface, and then do something dynamic and add another one. But I haven't experimented enough to know. If it does turn out that it's something that has to be sort of done at initialization time, then I've got a practical problem, because if it's started up and you're interacting with the forth, and then you need to maybe there's a way to restart the system. So I'll a thing on my list to investigate, because I'm interested in that kind of thing as well. Being able to have the several devices. I'm particularly interested in having the serial port going, and then still also having the flash drive going, because I think there are some interesting things that you could do with exposing the file system of the device at the same time that you're interacting with it over a terminal and so on.
Yeah, and so just to give some context to that answers, it's great that you're doing this all in C. That gives us access to all of the C libraries. And so there's a tiny USB C library which allows you to do all of that stuff, but it sounds like it's a bit tricky to actually use this tiny USB C library. Okay, so if you figure it out, great.
Yeah.
And then this synthesis stuff is really interesting. The Yosys synthesis doesn't really work for me, because to say I have some operations like compare which are really slow and some other operations which are fast, I'd like to, pause the CPU for a couple of clock cycles while it's doing a compare, and not while it's doing like a negation of bits. So be able to generate it all myself is really interesting, but maybe that's the ways down the road. But let me ask you a difficult question there, forgive me. What about simulation of the design?
So for just a binary simulation, actually, I actually think that the syntax that I outlined there, I've got actually, as I was sort of thinking through in my head, how would I generate the synthesis from this, simulation via that syntax actually might be easier than the synthesis, because there I only have to keep track of the set of connections and then cascade loop through them and sort of sort of tick forward time, and so it actually sidesteps the problem of where things are at. Now, if it depends on whether you want to incorporate properties of latency in the device. If you want to incorporate that, that's a whole other thing, and then you have to have knowledge of the layout and knowledge of the latencies. So yes, it's a concern as a yes. So I think it's would be possible to do some very basic synthesis that doesn't take into account how long it takes the combinational logic to stabilize. If you want to take that into account, I think it would get tricky fast. So.
Understood. Thank you.
It's a good thing to think. I've pondered that question a little myself. I'm like, well, I don't have a good sense. To be honest, I'm assuming that relative to the kinds of things that I would typically want to dynamically synthesize, I would imagine that you would sort of clock it much slower than would possibly have an issue. But then again, maybe I'm not being creative enough about what I want to dynamically synthesize. So.
The issue is debugging, so it's really easy to debug at the synthesis level, because you can track every signal, and a lot harder to debug at the it's easy to debug at the simulated level, a lot harder to debug at the synthesized level. So anyhow, thank you.
So let's say one is feeble-minded and one wanted to write code for the FPGA without spending a lot of money. What sort of tool chain is available at low cost or free?
So the FPGA. So I mean, future world, if I'm successful, you'll be able to do it in Forth. But for now, the tool chain.
You missed the feeble-minded part.
Indeed. So now, currently, there is a tool chain from called Yosys that supports this particular FPGA very well. Excuse me. It pretends to be Verilog, and so generates reasonable synthesis. Using it is the easiest, the easy, and this is a low sort of, I'm not sure it counts as easy. If you sync the Pico-iCE SDK repository, there are samples that include a Verilog file and a C file to sort of control them, and you can compile them as one unit and then deploy them on the device. And that might be the simplest thing to start, although that still requires git checkout, sorting out, syncing the right submodules. Probably you would need to be doing it on Linux or Windows subsystem for Linux. So not super easy at the moment, but then again, at least you're not using proprietary tools. So I can share links out if folks are interested in doing those steps, but it's not it is a non-trivial series of steps.
Yeah, at this point, it's just idle curiosity on my part. I remember James Bowman giving a talk on generating code for an FPGA that was all based on a tool chain that was free or inexpensive.
These tools are, I mean, to be clear, this set of tools that with Yoast is free. I'm just suggesting that it's sort of not. There's not kind of. I haven't seen a super simple tutorial, but it's not too bad actually. The website for actually I can even show that here. Let's see. The website for, if I go to
I think it's Yost's HQ.
Yeah, actually, I was going to say that even the website for the Pico-iCE itself is actually a pretty well structured thing. And so, if you really actually, if you're trying to do it sort of straightforwardly with this device, this is actually a pretty reasonable series of steps. So, excuse me.
May I also answer that question, please?
Please go ahead.
Yeah, so as somebody who's just been learning Verilog, it's a total pain. And also, particularly on the J1, I've been trying to do this single port stuff, mostly done. I'm kind of wrestling with the fourth now. The problem is when you're debugging a program, you're just doing one thing at a time. When you're debugging Verilog, there are like all these different things going on at the same time. So it's really a lot harder to debug. So there are a bunch of simple tools for doing these kinds of things. There are like some things that do C++ to Verilog. There's also a really nice graphical tool on the Pico-iCE. Forgive me if I don't know the name, but if you join their Discord server, and so it's possible to do some things on the FPGA using kind of streams or graphical editors and stuff like that. So for the feeble-minded, then I think that's really the way to go. Or find a friend who's studied Verilog. I remember the first day in Verilog class, I was like, this is completely non-intuitive because you're not actually programming, you're building a circuit. So it's, if you've had the electrical engineering training, you can do it. But the story is the beginners, and there are a ton of beginners in this area. If they do manage to do something, it's a real mess. Thank you.